Hey everyone, this is a short teaser about our paper Learning Hybrid Control Barrier Functions from Data. I'm Lars Lindemann, and this is joint work together with three students, Haimin from Princeton University, Alex Robey and Hanwen Zhang from Penn, Professor Dimos Dimarogonas from KTH, Stephen Tu from Google Brain Robotics, and Professor Nikolai Matni from Penn. So as a motivation of our work, let's have a look at the three shown systems that are all safety critical. While these systems may seem very different at first, I'm going to argue that they share some key properties that lets us reason about them roughly in the same way. First of all, these examples are all really data-rich in the sense that it's easy to get access to data exhibiting safe behavior. Second, the dynamics of these systems are inherently nonlinear and hybrid. In other words, these systems are described by both continuous flows as well as discrete jumps in their states. Such models are important and can capture contact dynamics, as well as bipedal locomotion and semantic logic in self-driving cars, as shown in the above examples. Third, and this is a very important property, in most of the cases, we have a pretty good idea of how to accurately model or identify the system dynamics. So in this work, we actually use this to our advantage and make use of the explicit system knowledge to learn provably safe control laws instead of resorting to the tedious task of analytically finding such control laws, which is often simply impossible for complex system dynamics. In this work, we use a hybrid systems formalism in which the continuous evolution of the state within a set C over here is described by this ordinary differential equation that can be controlled by the continuous control input UC. The discrete evolution of the state within the domain D here is described by this difference equation that can be controlled by the discrete control input UD. Importantly, we assume here that the hybrid system dynamics described by FC, GC, FD, and GD are known to us. What we also assume is to have access to a set of safe expert trajectories during the continuous and discrete evolution of the system. We then feed these two components into an optimization-based approach that we elaborate on in the paper that will give us the following. From there, we will learn a set calligraphic C that is safe, meaning that this set under-approximates the safe expert behavior, and second, that is controlled forward invariant, so that we can always select continuous or discrete control inputs that will keep us within this set. The contributions of this paper are threefold. First, we present hybrid control barrier functions as a means of synthesizing safe controllers. Second, we learn such valid hybrid control barrier functions from data. And third, we validate our findings on a compass gate walker. The second case study in the paper is a compass gate walker that is torque controlled. An energy-based controller has been used to collect safe expert data from which we have trained a two hidden layer fully connected neural network. Without a control action, the system is unsafe, as you can see, and the walker will fall. While when we use the learned hybrid control barrier function, the system is safe and the walker walks safely. I'd also like to show the two following plots. On the right, the energy-based controller is shown, and on the left, the controller based on the learned hybrid control barrier function is shown. Each dot over here indicates an initial position of the system. If the dot is blue, the resulting trajectory is safe, while a red dot indicates an unsafe trajectory. The zero-level set of the learned hybrid control barrier function is here and defines the safe set calligraphic C for everything that is inside. The first thing we can observe is that this safe set here, which is also shown over here, roughly under-approximates the safe expert behavior. The next thing we can observe is that most of the initial conditions within the safe set will result in a safe walk. Another observation one can make is that even if we start outside the safe set, the resulting trajectories are often safe, as shown over here, where in particular the energy-based controller fails, as can be shown over here. What we suspect here is that the attractivity properties of the safe set calligraphic C over here result in the fact that initial position starting over here will eventually enter the safe region. Lastly, I'd like to advertise our code repository, where you can find the code in order to reproduce our simulation examples, as well as the full article and an extended version of this talk.